Okay, on this slide is the resource that I record from the previous year. The first one, even though it is in Thai, it may help some of Thai students, is introduction to the mechanics of material. Okay, that is going to be like a 1.5 hour video clips telling you what important of this course, and when you finish it, what you can do with your knowledge and skill. And also another clip, the second one, I do some conclusion. This is going to be the second clip. This is the first clip on the knowledge on this subject from chapter 1 to chapter 5. And the third clip is the preparation on the midterm examination of the second term of last year. Anyway, hope you guys may come to visit it, choose them, and they may help you guys a little bit on preparing for this incoming midterm examination. So we have the midterm. Our midterm is going to be on January the 20th, and then it's going to run from 9 o'clock, 9 a.m. to 11 p.m. And it's going to be written examination. You guys going to have this kind of examination. That means you're going to follow what you did for your homework and prepare yourself in the way like that. And then you're going to follow the SUT rules and regulation, because this examination will be organized by the university, not me. Okay, and it's going to be 40% with 4 problems. You may visit the video clips that I show you guys last lecture. So that's all for the midterm examination. Do you guys have any question on this incoming midterm examination? Okay, quiet. Let me come back to what we have on the chapter 5. We're talking about the torsion, and then the torsion you can see from this graphic. We have the dive shaft. Dive shaft is the torsional member. Is uses to transfer the torsion from the engine and the transmission system to differential and to left and right axle to drive the car. For the real thing, it is on this like pictures. Okay, this is going to be the shaft, and you can see the shaft will have the circular section, and it can be solid section or it can be hollow section. The hollow section is the one that's more efficient when compared to the solid section. And from the previous lecture, we have the stress by putting the torsion into this shaft. You can see the shaft will twist, okay, like this. You may use your finger and you can twist it, you can feel it. The torsion will produce the shear stress, and the shear stress can be determined from the torsion times R divided by J. Okay, if you take the model of this shaft and then you put this symbol into the shaft, the symbol for the torsion going to be in double head, the arrow with double head. Ajahn, may I write the arrow with the one head arrow and this one circle. Yes, you can do it. It's up to you guys, but I prefer to do the torsion like this. And again, R. The R is going to be the radius of this solid section, and then R can be any length from the center to the outer layer of the shaft. And the last one, the J. J is going to call the polar moment of inertia. You know this guy from the engine static, and then it's going to be equal to pi over 2 r power 4 for the solid section. But for this hollow section, you have the radius, inner radius and outer radius. The J for the hollow section is going to be pi over 2 r sub o power 4 minus r sub I power 4. Okay, it's going to be the the polar moment of inertia for the outer portion. Let me take this one. That is going to be the polar moment of inertia of this material. And then if you prefer to use it with diameter, it's going to be pi divided by 32 d power 4. And for this one, it's going to be pi divided by 32 d sub o power 4 minus d sub I power 4. That is going to produce the stress across the section. Let me draw the stress distribution. Okay, if you guys has the positive, this called the positive torsion. But when the torsion in the opposite, this is going to be the negative torsion. The negative torsion gonna produce the negative angle of twist, and the positive going to produce the positive angle of twist. And then the stress that occur on this solid section will distributed linearly, is linear distributed across the section. Distributed is linearly distributed across the section. And if it is in the hollow section, is also in the linear, but most of stress distribute only on the material, on the outer layer of the material. So that's why this hollow section is more efficient than the solid section. And then you got the twisting, like you guys know about this. When you twist this one, okay, the radius will move. If you mark it like this on the section, it will move like this, and then it's produce the angle. This called the angle of twist, and the angle of twist is going to be the torsion times the length. This is the length of the shaft, and divided by G. G is going to be the shear modulus of elasticity. G is shear modulus of elasticity, and then it's going to be E divided by 2 times 1 minus nu. Okay, you can compute the G by using this equation also. And that's all for the knowledge that you are going to use in the examination. Okay, and let me talking about the power shaft. They are the shaft that's used to transfer the torque from the engine to the propeller of a ship. Okay, that's also involved with a chip, not only the car. And if you are a civil engineering student, later when you go to work, we'll use this kind of steel auger to drill the ground and to investigate the soil and rock layers under the ground. So you can use the result from this investigation to design the foundation of the structure. Okay, foundation of a building. That's for example. And then in the review, again, you got to know the function to determine the stress. And again, for this one, you may use the R or the rho, whatsoever you like. It's going to be the radius of the cross section of the shaft. And then if you consider this small element, okay, it's going to be the rectangular element, and then the square. And then you can see it's going to produce the stress. When the stress occur, they not occur only one. They will occur 4 of them corresponding to each other to make the element in equilibrium. I did mention this before. If you prefer, just go back to the previous lecture. And then T is torsion, and rho or R is radius. That J is going to be polar moment of inertia. And then we're going to use the angle of twist again. The angle of twist actually is going to be here. And it can be determined from torsion time length divided by modulus of elasticity, shear, modulus of elasticity, and polar moment of inertia. Sometimes we got to put the summation in front of it. If the shaft combined with different cross section or different material, and then just do the same thing. The polar moment of inertia for the solid section and the polar moment of inertia for the hollow section when C is going to be the radius. This is going to be R sub O. This is going to be R sub I. I prefer to use R because R is the radius, the low and C1. And then let me move a little bit to what types of problem do we have. Okay, for example, not for example, for this incoming examination, I like you guys to concentrate on statically determinate shaft. Why, Ajahn? We don't have much time to involve with statically indeterminate. No, most of the shaft we use in our engineering, okay, is going to be the statically determinate shaft. Like the example that I just show you guys. Okay, and there are going to be 3 types of problem. 1, the analysis. Okay, follow the equation we just mentioned. We can determine the shear stress. We can determine the angle of twist. Okay, and that is going to be the analysis 1.8. And I just show you guys one thing about the shear strength. I draw this model to show you guys before the torsion. You may draw the line like this. Let us fix this end, and after the torsion T, this one move, okay, from the green to the black, and we call this is the angle of twist. And if you project the line from this end to the fixed end, this one going to be the strength, and this is going to be the rate. Okay, and by considering the displacement occur here, you will get the shear strength times L is equal to the angle of twist times R. So the shear strain can be determined from phi times R divided by L. And since this is in the unit of radian, this also in the units of radian. This is meter, and this is meter. You can cut it. So the gamma and the phi going to get the same unit, and the tau going to be in the mecha Pascal. The G usually is going to be in the giga Pascal, and then the unit homogeneity must be important. If you use meter, this is going to be meter powerful. The L is going to be in the unit of meter. So beware about this. The second one, from this equation, you may do again the T, the 1 point B. We are going to determine the largest torsion. So there is two equations. You get two largest torsion. From this equation, the T is going to be tau allowable. This one will change to the allowable shear stress time what? Time J, and then divided by R. This is going to be the internal torsion. Is different from what they're asking us. This is going to be the external torsion. So separate it. Okay, you may find from the equation, but it's going to be the internal torsion. The same thing over here. The same thing over here. If you write this equation again, you will get the internal torsion equal to, this is going to be the allowable angle of twist. And then it's going to be what? The T, G, J, and then divided by L. So you got to use these two internal torsion to determine the external torsion based on free body diagram and equation of equilibrium. And if you get from the first one, you get the external torsion from this one, let's say 10.1 Newton meter, and based on this black torsion, you got the external torsion of 10.5 Newton meter. What is going to be the answer for the largest torsion that can be applied to the shaft? Guys, which one? 10.1 or 10.5? Which one? Natapong. If you do the calculation, okay, guys, oh, okay, T is going to be the smaller one, okay, even though they asked us the largest. Because of what? Because the torsion that's applied to the shaft will be increased from 0, 5, 6, 7, 8, 9, 10, 10.1. When it's reached 10.1, okay, the structure will consider to be failed by allowable, okay, and what? And this is the governing value of torsion that we use. And the last one, we're going to do the design. In the design, what we have is this equation must be rewritten, because when we design the chart, we determine the dimension. What going to be the dimension? The R and the J going to be the dimension of the chart. So you just say J over R. That's you are looking for, okay? And J over is going to be equal to the T maximum divided by this one divided by tau allowable. So they will give us the tau allowable. If they won't give you the tau allowable, it's going to be tau sub y, or yielding shear stress divided by factor of safety. Okay, and then you may use this one to determine the diameter of the shaft. Anyway, you have this one also, okay? And then from this equation, you are looking for the J. So that's going to be the J equal to TL over G, and phi allowable. They are going to give you the allowable, okay, angle of twist. And then basis on this, you got another diameter. Let's say from this one, you got 25 millimeter. And then basis on this one, you got D equal to 22 millimeter. Again, what you are going to answer for the design? 22 millimeter or 25 millimeter? Which one? Which one? When you decided, which one you're going to answer? 25 or 22? Based on the safety of our structure. Okay, you guys, which one? Virgo, which one you like to answer? Based on your design.
The larger.
The larger. Okay, thank you very much. You're going to select this one because you like to have a safe shaft that can resist the torsion, okay, with the strength, with the large strength and large stiffness. So you select the 25 millimeter. That's the principle you guys going to use, okay? The torsion, select the smaller one. The diameter, select the bigger one. Now, that's why we design the shaft. We prevent the failure, okay? This kind of failure may cause the loss of, life or money, okay? And this is a kind of ductile failure. Ductile failure occur in the steel shaft. Steel shaft. We're going to prevent this one. For the design, okay, we're going to prevent this one. And then the mechanical engineering student, some of you guys going to design the engine. Again, the new world going to have the electric car. The motor in the car also have the shaft, okay? You guys still involved or work with the shaft, even though the car changed from the gasoline engine to the electric motor. The shaft still in the motor. So you guys, you're going to work about this. This is the real thing. Okay, this is the model of the engine to have you take a look at this camshaft for the gasoline engine. This camshaft is used to open the intake valve or the exhaust valve. Let me move to example. We are going to work on analysis 1.A, analysis 1.B, and we move to the design for our lecture. Let us have the hollow steel shaft. This hollow steel shaft has the outer diameter of 40 millimeter and inner diameter of 30 millimeter. So you guys are going to use the knowledge of engineering graphic, and you can draw the section of this shaft to be this figure. Okay, this is going to be the D sub O. This is going to be the D sub I. And you guys are supposed to know this is going to be the thickness, and this is going to be the thickness based upon engineering graphic. You may have two of the thickness equal to d sub O minus d sub I, or the thickness is going to be d sub O minus d sub I divided by 2. So that is going to be d sub O divided by 2, d sub I divided by 2. That is going to be r sub O minus r sub I. Okay, then if the G is 75 gigapascal, they ask us to determine the tau max and determine the phi max. Okay, when we talking about the tau max, and you can see the cross section of the shaft is going to be the same. So the tau max will use the r max divided by j. Since the radius and the j are constant across the shaft, so the tau max will be based on the torsion T max, and this is going to be the internal torsion. You can find the internal torsion by the free body diagram and the equation of equilibrium. So our first step, we will find the internal torsion, but following this slide, we may start by finding the J. So what is going to be the J? For this one, is up to you. It's going to be pi over 2 r sub O power 4 minus r sub I power 4, or it's going to be pi 32 d sub O power 4 minus d sub I power 4. It's up to you. Okay, and if you put it in this one, that's you going to use the equation of this, because this is 20 millimeter change to 0.02 meter, and you will get J in the meter power 4. When we get the J in the meter power 4, most of the time in this unit, the magnitude of J going to be small. Okay, but when it is in millimeter power 4, the magnitude of it going to be big or large. Please take note on this. Now we move to the next slide by using the free body diagram and the equation of equilibrium. You just cut this portion, okay, and you take this portion and dock it over here. That is going to be the portion for the GC. On basis on this, I'm going to ask you, you may set this one as the x-axis. Okay, you may set this one using the right hand rule, the x, y. This is going to be y-axis, and this is going to be C. In Thai, we call it Z. It's a C in American English. Okay. Anyway, by doing this, you also got to know the G. G is going to be the frictionless bearing. You know the bearing, right? If you don't know, go to your motorcycle. In the wheel, there is the bearing that lets your wheel rotate when you drive the motorcycle. So the G and B is going to be frictionless bearing. By doing this, another thing you got to do, in my opinion, what going to be the direction of the torsion? Okay, you're going to find the direction of torsion. Use your right hand, and then for the 40 Newton meter, you use your finger. Follow the arrow over here. Use your four finger, and then you just do like this, and the thumb gonna tell you the direction basis upon this. I got this one for 80 Newton meter. By doing this, it's going to help, in my opinion. How about 160? For the 160, you do another way. It's going to be in the opposite of the of the 480, and then you come to the 240. For the 240, you can see it's going to be in this direction, the 240. And then for the 550, it's going to be in this direction. So you have various torsion basis on what we have over here. However, when you cut for this portion, there is no torsion. Since there is no torsion over here, there is no internal torsion. Next, you cut over here. Okay, let me say the T sub GC is 0. And then you do the cutting for the next portion. Okay, just do a small drawing. And I again prefer to put 480 by this double head arrow. And since 480 is in this direction, so the resistant torsion summation of the moment about x equal to 0. This one T sub CD, this one is going to be positive. So T sub CD is going to be equal to 480 Newton meter. And then cut another one. By cutting another one, this is still 480. And this is the yellow one is 160. So put this one. Since 160 is smaller than 480. So by doing this, I'm going to put the torsion in which way? In which way? In the yellow way, okay? To make it, you do the summation of the moment about x equal to 0. T sub DE, this one, okay? You set this direction is positive. T sub DE plus 160, and then it's going to be equal to 480 Newton meter. So the T sub DE is going to be 320. Now, you may cut the next one, but I don't think you're going to use the BCAD. You're going to cut it in this way. It's going to be a little bit easier to draw the picture. So this is going to be the torsion of 560 Newton meter. Since this one is in this direction, so the torsion of this summation of the moment about x-axis is going to be 0. Just put in this direction is positive. So T sub EF is 560. Then what we have for this one, I should tell you that this is going to be the positive torsion and is going to produce the positive angle of twist. Let's say this is going to be positive angle of twist EF. This is positive torsion EF. And this one also is positive torsion because the arrow point out. Okay, and this is going to produce positive angle of twist DE. And this one also, this is the positive torsion, and then the angle over here, let's say CD, is going to be positive. Then you may use the internal torsion and then draw the diagram. So the first one, this one is the purple, is the pink, okay? This is 0. The red is going to be 480, and the green is going to be 320, and this one is 560. And you know that the tau max gonna proportion to the T max for this problem. Since what? Since R is constant, J is constant for the whole length of the shaft. So 560 gonna produce the maximum torsional stress. Just put them into the equation, and let me tell you again, since this one is Newton meter, so the radius over here must be in meter, and the J over here must be in the meter powerful. So you will get the shear stress of 65.2 megapascal, and this must be less than, actually in the design, actually less than tau allowed. Okay, so if it's less than tau allowed, for example, it's 75 megapascal, this is okay. But if this one is larger than tau allowed, the problem going to be no K. You got to redesign the section by this one. You got to get a bigger section. Okay, that is going to move to the design problem. So let me take a note on this portion. Okay, by doing things like this, you guys are going to invoke it in the design problem. Since it's less than tau sub y, so the still is okay. Okay, but I think it's supposed to be less than tau allowable. Okay, not tau sub y. Then the angle of twist, like I told you guys, is going to produce positive angle of twist to all of them, since they are positive torsion. Okay, they are positive torsion, except this one, the phi sub, what this one, GC, going to be 0 because there is no torsion. So this one can be separated into 4 portions. The first portion is 0. Since the G, the material is the same, and the cross section of the shaft is the same. So we have phi of point G reference to point F. Phi G / F is going to be the 0 over here. This is phi, this is C / G plus phi, the next one A / C plus phi, the next one, this one E / D plus phi F / E, and then you know this one is going to be 0, and the other GJ are constant. So only the TL, this is going to be this portion, and the next one is going to green. So this is going to be 3L for this one, and the last one is going to be blue. So for this one is going to be TL. This is 2 meter. This is 1.5 meter, and this is going to be 2 meter. So follow the unit Newton and meter, you will get the angle of twist to be 0.1987 radian, and it's going to be clockwise because this is going to be positive phi. Okay, and then you may say it's going to be in this direction. Okay, actually it's going to be in this direction because this one is positive. When it's positive, the arrow just point out from the shaft, and then you may convert it into 11.4 degree. How? You know that pi, that is half of the circle, is going to be equivalent to 180 degree. So 0.1987 radian is going to equivalent to 180. 0.1987 divided by pi. You get this to be the degree. That is analysis 1.8. And then we move to the analysis 1.b. This problem is a little bit trickier. We have the solid shaft, two of them. One is going to be A, E, F, connect by the gear B. Okay, this solid shaft D, C, connect by the gear C. Gear C is smaller than the gear B, and the shaft has 20 millimeter diameter. So find the maximum torsion that can apply to this one. So basis upon this, you may use your finger and you can see this torsion is going to be point out torsion is going to be positive external torsion. Okay, this is going to be actually maximum external torsion. So basis on what? This one basis on the angle of twist, not more than 0.1. Okay, again, if it's basis on the power allowable, yes, it can, but you supposed to go back to the previous lecture on the last year midterm examination. They asked you analysis 1.b to determine the torsion T, but that's problem basis on the tau allowable. Okay, so by doing this, phi equal to TL over TJ. Okay, we are going to find the T. The T is going to be phi allowed, and then GJ divided by L. So you got to use this one, but this internal torsion is not easy to determine because we have the gear. The gear is going to be something like a small cone and a big cone. Okay, based on this, you got to know when the large cone move. Okay, 1 unit. The small one going to move more than 1 unit. Okay, you can do the experiment at your dormitory talking about this. If this one rotates for 0.1 radius, this one will rotate more than 0.1 because the smaller must move more than the larger gear. Okay, based on this, we have the J. Okay, it's going to be equal. Just put them together. The J is over here. It's going to be this number. So this is first one. But the G also 80 gigapascal. So the G also constant for these two shaft. The G and the J are constant. But it's going to talking about the length. The length 2 meter and 1.5 meter. And then the gear also involved in this calculation. So first, we find the internal torsion in the shaft. The torsion T going to produce everywhere in this shaft, in this orange shaft, in this AEFB shaft to be T. So the torsion over here is going to be T. But due to the gear, okay, it's going to produce the force of F, in which the T is going to be 150 millimeter times F. So this is going to be 0.15 meter times F. And this force will be act on the small gear, okay, by the force of T over 0.25. This is going to be T over 0.15. It's going to produce the torsion in this CD shaft. So for the CD shaft, we're going to have the torsion equal to this force times 0.075 meter. Then the torsion occur over here is going to be 0.5 T due to the gear B 2 times larger than gear C. The torsion over here reduced to 0.5 T. Now we're going to compute the angle in the shaft, yellow shaft. Why? Because this is the reference support which is fixed. Okay, since this is the reference, the rotation or the angle of twist SD, the angle of twist SD equal to 0. Since this support is fixed support, so we will start over here, and then due to 0.53, we're going to compute the angle of twist between CD. So by doing this, 0.5 T gonna produce the angle of twist in this yellow shaft. So this is 0.5, and the length is 1.5, and GJ gonna be constant. So just put everything together. For this twisting, we get 5.968 10 minutes 40. That is the angle of twist that occur in this one. From this one, if you mark it, then this one has this rotation, and this is going to be phi C/D. That's also occur on the small gear C. And then the rotation that occur on this section, the rotation, the light blue rotation, is also going to occur on the larger gear by putting this one rotate. Okay, rotate what? Rotate in this light blue. So this is going to be the light blue. This is going to be phi C/D. Okay, and sorry, this is going to be phi C/D. And then the distance is going to be the same on the bigger gear. So the big distance is going to be phi R. Okay, phi C/D, R sub C. This is going to be R sub C. The distance is here. And this distance gonna occur on the larger gear. Okay, and then it's going to produce this angle of twist of what? Of phi of the distance. The distance is going to be phi sub CD R sub C. So what we have, we are looking for the angle of twist at D. Okay, at D. So the equation over here will be angle of twist equal to distance divided by another R. This is R sub B. So the same distance gonna divide by the larger radius, and the angle of twist reduced by half. Then what we have is the angle at the bigger gear. And then the shaft, the orange shaft, also need to twist. So we combine the result from the previous calculation. Okay, this is half of the twist occur on the small gear, and then we're going to plus it by the angle of twist of this orange shaft. So we just do that. We have the torsion over here for T and 2 meter and GJ. So that is going to be the total angle of twist occur at this point compared to at point D that we has fixed, and then it's going to be 0.1. This will be 0.1. Let's me go back to this one. Yeah, it's going to be maximum angle of twist. It's going to be 0.1. So just put the 0.1 here. You get the maximum torsion to be 52.9. So by basis on the angle of twist, this is going to be 52.9 Newton meter basis on the angle of twist. That means it's based on the stiffness of the shaft. Okay, this is based on the stiffness of the shaft. And then find the maximum shear stress. Maximum shear stress will occur on this one because this is T. This is 0.5 T. So it's going to be on the orange shaft. Okay, and then just put it into the equation. It's 33.68. Okay, anyway, it's less on tau sub y. If you compare by the tau allowable, that is going to be 50 megapascal. It's going to be okay based on the design. Based on this, it's going to tell us it's going to be in the linear elastic behavior. Okay, this comparison based on the design. Okay, this comparison based on the behavior of the material. Okay, now we come to the next in the design. We have the board. Our board have the shaft that connect the engine to the propeller. The shaft has the length of 15 meters. The torsion from the engine is 10,000 Newton meter. The shaft is the hollow shaft, has the internal diameter of 200 millimeter. So the shaft is going to be something like this, and this is going to be the sub I of 200 millimeter. The top here is going to be D sub O. We are going to find the D sub O. Okay, and then have the yielding stress of 80 megapascal. Have the shear modulus. This is going to be G. Okay, this is going to be tau sub y. You're going to find tau allowable. It's going to be 80 divided by 4. That is going to be 20 megapascal. We use a big safety factor because it's a ship. It's going to subject it to the salt in the sea. Okay, corrosion is large. So we can use large factor of safety to prevent that kind of corrosion. And then the maximum angle twist is in the degree unit. You got to change this one to the radian. Okay, and then you find the thickness. So that means you're going to find this one. Okay, the T is going to be R sub O minus R sub I, or you may T is going to be D sub O divided by 2 minus D sub I divided by 2. That is going to be thickness. So we have these three equations, and then we got to decide it based on tau allowable. That means based on the strength. And then we also decided based on this one. This is based on stiffness. Okay, this is going to based on the strength of the material. So we will compare the thickness from the strength with the thickness calculated from the stiffness, and we're going to take the larger one. Then we have this one, and then the J going to be this one. We don't know the R sub O because we don't know the D sub O. So J is unknown. and the R sub I. You can put the R sub I into this equation. Okay. And what we have is the free body diagram and the equation of equilibrium. So we can find the internal torsion of equal to T. And then based upon this, we use the tau allowable. That is going to be the strength design. And then the tau allowable is 20 megapascal. From this equation, this is tau allowable. T is going to be the unknown. This is going to be, no, T is unknown. T is going to be 10,000 Newton meter. Just put this one. The outer radius is going to be this one. It's going to be R sub O. And then you put the J. You solve the equation. Okay, this is R sub O power 4. You get the radius to be 107.6. So the diameter here is going to be 215.2 millimeter. Then the thickness, you just minus R sub O with R sub I. Based on the strength, you get the thickness of 7.6 millimeter. Okay, not enough. You got to check for the stiffness. Based on this angle of twist or the stiffness, we change 360 degree. Oh, this use 2.5. So this one, you may use this one, 2.5. And then you just change it to radius. Okay, do the proportion. By doing this, the angle that's allowed here, you know, it to be this one. Then the T is going to be here. The length in meter, the G, and then the allowable. You take the J required up, take the phi allow down here, and then you solve for the radius. This one is going to be 106.3 outer radius, and then the thickness is 6.3. So the thickness that we going to use is going to be the maximum one. So you use 7.2 millimeter, and following this, you can check the thickness of 7.6 millimeter. This is going to be the problem of the analysis 1.8. Based upon this one, what is going to be the phi? So that is going to be 2.01. Yep, this is thick. So the angle of twist smaller the allowable. This is the old examination many years ago. So I put it over here for you guys to reference. Next, in the design, again, we have the same problem as the analysis 1.8. We come to the same thing, okay, the diameter. But in this design, the tau allowable, this is going to be based on the stiffness is 150 megapascal. The allowable angle of twist is 0.192 radian. We teach this one, and then we design the example from the previous example, the board. Okay. Anyway, the concept going to be the same. We're going to determine the D sub O. This one is not the thickness, as we want, based on this one, and based on this one, and then we select the larger one. In this design, the section is going to be here, and since D sub I equal to 0.6 D sub O, so this is going to be 0.6 D sub O. So the J is going to be the function of D sub O. By doing this, we have basis on allowable shear strength and basis on allowable angle of twist. This is strength design. This is stiffness design. The same thing. We got to determine the torsion, and the same torsion we have is the same diagram. The maximum torsion is 560. So we use this one to design the D sub O basis on tau allowable. So this is going to be 150 megapascal. This is going to be our 560 Newton meter. So the J over C is going to be what we're looking for. And then we got the external diameter of 27.95 millimeter. And then they said it's 28 millimeter based on the strength. And then based on the stiffness, the angle of twist must be the combination of the twist of every section GC, CAD, DE, EBF. And then the angle of twist that we did calculate is in the form of D sub O and is equal to the allowable angle of twist. You solve this problem to get the D sub O. You get this one for 38 millimeter. For the safety, you select 38. Okay, and then the answer is 38 millimeter as we need it. And then we come to the next portion before we break our lecture. The shaft, okay, also used in the generator and dive. This one called the power shaft, okay, that's going to link between the generator, okay, passing to this one. This is actually the engine. Passing to this one, this is a generator to produce the electricity. But for the power shaft, as I show you, and the same thing, even though in the dive shaft, also, when you buy a car, okay, you got to go to the car dealer and you are going to buy a pickup, right? When you buy a pickup, what is going to be the horsepower of the engine, okay, at a given lap per minute of the engine? That is the thing that you usually to ask in the dealer. You asking for what? You asking for the power of the engine. Even though the engine changed to the electric motor, you still talking about the horsepower. That is going to power. Power is going to be the work divided by time. And what is going to work? For the engine, the work is going to be the torsion times the angle of rotation. And then when you divide the angle of rotation by the time t, this is going to be the omega, which is the angular velocity. Okay, this is going to be angular velocity. Okay, and then the equation that you're looking for is the power. So when you're talking about this is going to be the velocity, but the velocity here is going to be radian per sec. Okay, how you can change it to be the lap per minute. Okay, I give you to be the homework. If you don't do it, when you are studying in the machine design, next course from here, you're going to do so. But this one, we don't care much about this step. We will let you study further in the next course. And also, the 746 one is called 1 horsepower. So from this one, you can convert the power of the, let's say, motor over here to be the horsepower if you prefer. And then the frequency of the shaft rotation is going to be the angle velocity divided by 2 pi. So the power also can be determined from this equation. So in the machine design, you may determine the torsion by the power divided by angular velocity, or the power divided by 2 pi frequency. But in our subject, most of the time, Ajahn will give you the torsion such as it's going to be 1000 Newton meter. Okay, and then you can use this equation to determine the solid shaft radius of the solid shaft. You can derive this one easily. Let me move to this example. We have the electric generator. You may go to the Akhar Rin Room 1, the academic building 1 over there. And then on the sides of the Rin Room 1, there is this system to be the backup power in case we have the electrical breakdown in our electrical system in our university. The shaft is the circular steel shaft with 1.2 meter length, okay, and external diameter is 400 millimeter. The engine has the angular velocity of 100 radian per second. So from this power and omega, you can determine the torsion. Okay, but in the examination, Ajahn will provide you the torsion. And then you find the thickness of this shaft, when the tau ultimate is 200 with factor of safety of 2. So you're going to have the tau allow of 100 megapascal. And the angle of twist is 3 degrees. The problem is similar to what we have in the chip from the previous example. So we do the design one basis on the shear strength or basis on the tau allowable. Another one, we will do the calculation basis on the stiffness or based on the angle of twist. So the tau allowable is going to be 100 megapascal, and the tau allowable will follow this equation, and T can determine from the power divided by angular velocity, that is 500 Newton meter. So you take the J up, it's going to be TC over tau allowable, and you know the C is going to be half of this, is going to be 20 millimeter. You put everything in unit of Newton meter. This is meter, and this is going to be Newton per meter square. You got the J, and then this J is going to be equal to pi over 2, and then you solve it for the R sub I. That is going to be 17.6 millimeter. This is going to be 17.6 millimeter. So the thickness is just minus 20 by 17.6. You got 2.4 millimeter thickness. Okay, and then for the angular velocity over here, you got to change 3 degrees to the radius by using this converter. Okay, and this is 500 Newton meter. The length is in meter. This is going to be G in Newton per meter square. You got to have this one. Do the same calculation. You get R sub I 16.2. You minus 20 by 16.2. You get 3.8, which is larger than 2.4. So you select 3.8 as the least thickness for this chart. It's going to be the same as we have for the chip. Okay, so that's all for you guys for the midterm examination. Okay, let me wait for 5 minutes. Okay, on next portion of this course, we will talking about the statically indeterminate torsional member or statically indeterminate torsional shaft. You know that from the previous example, we use the free body diagram and the equation of equilibrium to determine the internal torsion, and this internal torsion used to determine the stress and used to determine the angle of twist. But for this part of this chapter, our structure cannot only use the free body diagram and equation of equilibrium. For example, we have the shaft that fixed as A and also fixed at B. That is going to be the reaction T sub A and T sub B as the fixed support. And when you do the summation of the moment about x-axis, by putting this direction is positive, you have one equation. That's not enough to solve for these two unknown. So you got to require to have the compatibility condition, and then you got to use this equation, the torsion and angle of twist relationship, to make another equation. By doing this, you may see, by notice or observe how the shaft behave. Okay, we will have the angle of twist at point A with respect to B is equal to 0. But you may see this portion AC that's subjected to the torsion T sub A is going to have this torsion, and also if you draw this portion, there is also the same torsion T sub A. That is what you're going to have, this positive phi C slash A, and you have for this portion, this is positive D slash C. Okay, and if you draw this portion, the torsion T sub B is here, and then you're going to have the internal torsion over here. That is also T sub B, but this one produce negative angle of twist D slash B. By doing this is going to be phi C slash A plus phi D slash C minus phi D slash B, and all of them is 0. When you put this into this equation, you will get another equation. You can solve two equations for two unknowns, T sub A and T sub B easily. And then compared to this one, this is going to be statically determinate. Okay, you know the T sub B directly to be equal to the apply 50 Newton meter. You can see this 50 Newton meter gonna be in this direction, and you just do the summation of the moment about x equal to 0, T sub B equal to 50 Newton meter. Very simple. But anyway, there is the uses of this one. Okay, in the next course, when you talking about this, first we draw the free body diagram again. For this one, it's simpler than before. This T is coming from this angle, and then the T sub A and T sub B must be in the opposite direction of the T. So summation of the moment about X axis. Actually, most of the time we set the X in this direction and we put in this one is positive. No, this one is going to be negative. The T is positive. If you put something like this, it's going to be minus. If you put, it's going to be the same thing. So this is not enough. You got to make the compatibility equation from the deformation of the shaft. So the phi at A with respect to B is 0. By doing this, you got to cut two portions. Okay, the T sub A is going to produce the direction of this torsion. So this is going to produce the phi of, let's say, C/A. And this one, the torsion putting in, okay, this is going to produce the negative C/B. And all of them, one is out positive, one is in is negative. You may put them together. For this one, positive T sub A, L sub AC, and then GJ. Another one, you just put it into this one, and it's going to be T sub B and L sub BC, and then GJ. And then you just cut this one, you get the T sub A. You put the T sub A into this equation, you get T sub B. Okay, that is simple as before. Since the concept of this part is similar to the axial force, that's why we only make the indeterminate axial load member as the example problem, as an examination problem in our midterm examination. But for this one, we use the statically determinate. Now, coming into this one is going to be the solid steel shaft, have the shear modulus of elasticity of 75 gigapascal subjected to the torsion of 100 Newton meter. And if you use your finger, okay, rotate in the same direction, you will get the 100 Newton meter in this direction. And then they ask us to find the maximum shear stress and maximum angle of twist. That is going to be the problem analysis 1.8. And then they separate it. Okay, if the tau allowable is 60 megapascal, they ask us to determine the allowable maximum T. This is second portion of the problem. So this is going to be analysis 1.B. So what it means is the statically indeterminate shaft also can be analysis 1.A and analysis 1.B. Okay, but we're going to do the same thing. Free body diagram and equation of equilibrium to determine the internal portion. Based on this free body diagram, all the torsion passing to the centroid of the section. If you do the summation of m sub x equal to 0, putting this one as the positive, this is going to be x, this is going to be y, you're going to get this equation. Okay, T sub A plus B equal to T, which is going to be 100 Newton meter. Then compatibility condition. This one similar to the first slide for this lecture, for this portion of the lecture. So we separate this one into 4 portions. One is going to be for this portion. The pink is going to be T sub A. And then it's going to be T sub A times 100 and change into 0.1 meter. And then G. Why they put the number into this? Because the whole shaft made by the same material that's going to cut later. So don't need to put it in the number, just put it in the symbol. And then the diameter here is 12 millimeter. So the radius is 6 millimeter or 0.006 meter. Then you cut the next portion of this one. And for this one, let me put it. You're supposed to dock it in the different position, but I didn't have the area. So let me put this one for the second free body diagram. And then what is going to be this one? This one going to be T sub A as before. And 200 millimeter is 0.2 meter. And then G, J. And then the last one, you may cut in this portion. And you only draw this one. This is going to be the negative because the internal torsion pointing in. Okay, this is pointing in. So it's going to be negative T sub B. And then 0.3 meter and GJ. So the G can cut as I mentioned. You rearrange the equation, you can get T sub A equal to 0.144 T sub B. This is pretty small, 0.144 T sub B. T sub B taking a large portion of that. And then if you solve this equation, this is equation number 2, you may take T sub A, this one put into here. So it's going to be 1.144 T sub B equal to 100. Okay, so T sub B is 84.4. T sub A is going to be 12.6. So this is 87.4 Newton meter. This is going to be 12.6 Newton meter. Since this AC and CD from the free body diagram, they're going to take the same T sub A. Okay, the maximum torsion will occur in this portion. Okay, because the J is smaller, tau equal to TR over J. For the small J, going to produce large tau. That's why the TA will govern the shear stress for the CD. And the other portion, since the T sub B is large compared to T sub A, we may compute the shear stress that's occur on this DC portion. And then we compare tau sub BD with the tau sub AC, okay, to find the maximum shear stress. Then just compute tau sub AC, T sub AC, the radius for the small one, and the J, you got 37.1. For the larger one, 84.7. This is going to be the 12.5 millimeter radian in the meter unit. And then you get the largest stress occur on the AC. Okay, and then it's lessest on 60 megapascal. Is linear elastic and is okay for safety. Okay, for safety, for design. is less than tau allowable. And then the next portion, this is going to be analysis 1.A. For the analysis 1.B, we not finished yet. Analysis 1.A, we come to find the stress. Okay, then ask us for the problem. So we find the angle of twist of the AC, the maximum stress occur over here. So phi sub CA is going to be T sub A, and length and GJ. You put it into this one. That is going to be 8.25 10⁻⁶ radian. And then for the BD, for BBD is this portion. I put it in the light blue. Okay. Put it in the portion for the light blue. So you just put this one for the equation that we have. Actually, we just take the equation from here. This is phi d/b. And for the previous one, we can take from this equation. We didn't make another new one, just use the old equation that we have. So we have this one for phi d/b. We have this one for phi a/c. This is positive. This is positive. This is negative. Okay, and then we also can determine phi c/d, because what? Phi a/c plus phi c/d equal to phi d/b. If we know this one, we know this one, so we can find this one. So let it be your homework. Go back and take a calculation of this. And then for this one, this is going to be the largest, okay, angle of twist, because this one equal to the light blue plus the green. And the next step, can you calculate it in the degree unit? And then you can see that it's very small for 0.52, very small angle, less, that's half of the 1 degree. Okay, and for the design, for the analysis 1.B, not design, 1.B, we can find the maximum allowable T. This time they set up tau allowable to be 60 megapascal. Okay, and then the maximum stress occur in the AC. Okay, and then this tau allowable, tau sub AC, is going to be the tau allowable. We're going to determine T sub A. We rearrange our equation. Just put everything together. The T sub A is 20.4 Newton meter, and we have the T sub A equal to 0.144 T sub B. So the T sub B is going to be 141.4. When you combine T sub A plus T sub B by the equation of equilibrium, you get the maximum allowable torsion that can apply to this one for 161.8 megapascal, and it's going to produce the shear stress. Maximum shear stress occur here to be 60 megapascal. So it's like go in a different direction. The previous one give us the torsion, external torsion, and ask us to find the tau max. But this one give us the allowable shear stress and ask us go back to find the external torsion, which is allowable external torsion. And then this one also another example. Okay, find the torsional reaction as A and B. The problem is going to get a little bit harder because there is two external torsion, but don't worry, that's going to be the same thing. There is going to be T sub A and T sub B, and you put it in the same direction. The T sub A is going to be you put your hand like this. It's going to point in this direction. the same as the T sub B, point in the same direction. And since you put this one in positive, T sub B is negative, T sub A is negative. And then you take a look at this one. The 500 is negative. The 800, no, it's going to be the positive. Follow this direction. That's it's going to be a little bit harder, okay? And then you do the summation. This is going to be the first equation. Again, the compatibility, the rotation of A with respect to B is 0. And by considering this, you have this is going to be the first portion, and this is going to be the third portion, and that is the middle. Okay, this is going to be dA, right? This is going to be the third portion, and this is going to be the first portion. And then phi equal to TL over TJ. That's why you got to cut, okay, this portion to determine the internal torsion. Cut this one to find internal torsion and cut this one. By doing that, we cut this one, we get the T. Let's put it in what? In the green, okay? In the green, we put it. That is going to be in this direction. And then what we have, this one, the going to be the T sub B. Okay, you can do the summation of M sub X equal to 0. T sub this portion, you may call it for BC. T sub BC. This is CB. T sub BC. T sub BC. BC is here. It's going to be T sub B. And then this is pointing. This is going to be negative. Okay, T sub B time L point to, and GJ put it into the symbol because all of the shaft have the same section and built by the same material. Okay, and the third one, what we have is this one is going to be T sub A. Okay, and the 500 we also have in this direction is point out. So for this portion, we can determine this one, summation of M sub X equal to 0. This is going to be the portion of dA. So T sub dA is in this direction opposite to the red and green, equal to T sub A plus 100. So this guy going to produce the positive, okay, positive. Point out is going to be the positive. No, not the A, sorry, not the A. Okay, I'm wrong. It's going to be in between CD, not the A. This is going to be the CD. This is going to be the second one. It's going to be this portion. Okay, they use this portion to draw the free body diagram. So this is positive because it's point out and have the length of 1.5 and GJ. The last one is going to be easy because only T sub A is going to be involved. Summation of X sub X equal to 0. We're going to get T sub dA equal to this one, T sub A, and it's point out. So it's going to be positive, okay? And T sub A times 0.3 and GJ, cut the GJ, you get this equation. You solve this equation from the equation of equilibrium. You get T sub A as the negative. Now, this is not correct. So the real thing, the T sub A must be in this direction. The T sub B is okay. T sub B. T sub B is going to be 6 45 Newton meter, but T sub A gonna be this one is going to be 345 Newton meter. So you got to compute inside it. So T sub BC is going to be 645 and this one going to be in the opposite direction. Okay, this one is going to be 345 Newton meter. So just change the direction. This is going to be what I did show you, going to be the pocket. But for this one, you got to do the calculation. Okay, this is going to change to in opposite direction. This is 345 Newton meter minus 500. So we got this one to be the point out of 155. So the angle in this portion is positive. Angle of twist, this one is negative, and this one also has the negative angle of twist. So if you like to find the angle twist, you get the direction like this. The problem asks us to determine the maximum shear stress. Which one going to produce? Since J R is the R constant, okay, the same R and J. That's why the maximum torsion will govern the tau max that is going to occur on this portion, and then tau max is 645 times R over J. That is 410.62 megapascal. Is supposed to be less than 1,000 watts. And then find the angle of twist of the CD. This is going to be the CD, and the angle going to be positive. Just put it into the number. It's going to be 0.1974. Okay, and the last one is the composite charm. This charm made hollow by the steel. This portion, the red portion, is by the steel, and the inside gonna be the brace. Okay, the inside gonna be brace. So by doing this, that is two material working together. Assumption is the steel and the brace gonna connect perfectly. Okay, it's going to work together, connect perfectly. When they build it, they're going to heat the steel. Okay, when it heat the steel will get bigger, and then they put the solid brace inside it and cool down, and then it's going to stick to each other. The torsional reaction. So by doing this, you may see the 220 Newton meter. If you put your hand like this, you can see this is going to produce the 250 Newton meter in this direction. So at this portion, you will have this one for the steel and another one that's for the brace, T sub B R. So summation of F sub Y equal to, sorry, a moment, with the X direction by putting this is going to be positive. So they put in this direction is positive. 250 Newton meter or Newton millimeter, which one? I'm not sure. It's going to be Newton meter. Okay, it's going to be positive, and T steel and T brace is going to be negative. The compatibility, you may observe this one is fixed. Okay, support. The rotation that's occur over here gonna be 0, and this one is the free end. Okay, the rotation of the brace, the core over here, and the rotation of the steel, they are going to be equal, because as I said, it perfectly stick and work together. So we get this. So putting the torsional angle for the phi of the steel, the J will come from the hollow section, but for the phi of the BR, the J is going to be the solid section. So beware about that. And the L is going to be the same. You can cut the L, and then you may get T of the steel is going to be 33.33 times T of the brace. That means the outer, the hollow steel take large portion of T. Okay, that's follow what we have discussed. The hollow section is more effective than the solid section. And then you put it together, you get T sub BR of 7.28. And then so for the T sub ST of 233.3 times to 42.72. And then you can compute the stress that's occur on the section. And again, you can see most of the stress occur in the steel. You can compare by this area, which the area of the brace that is quite small. Okay, and that's we explain about this. And then due to the perfect work together between these two materials, the angle of twist must be the same. This is going to be phi BR equal to phi sub ST. Okay, you may compute for this angle of twist, and I give you as the example. Okay, what's the angle of twist? And then the stresses occur on this section in this direction is less than yielding stress. So it's going to be linear elastic behavior. That's all for chapter 5.